introducing you, sir. Dr. Rajesh Bhat, Assistant Professor, Vellore Institute of Technology. He did PhD from BITS Pilani in 2015, and after he did first postdoc fellow from NUS Singapore and second postdoc fellow from HRT Shenzhen, China. He published total 14 research papers in international journals and conferences. And his active research area are fluid dynamics, simulations of fluid flow, numerical analysis, and number theory. I welcome you, sir, in this session from the Department of Mechanical Engineering, Nawab Shah College of Engineering and Technology. Over you to you, sir.
Yeah, good morning to all. This is Dr. Rajesh Bhat, Assistant Professor in Department of Mathematics, VIT Vellore.
Yes.
So, first of all, I would like to thank the management of this Nawab Shah College of Engineering and Technology, and especially thanks to Professor Hussaini for inviting me to give this talk on this topic, aerodynamics of Bluff bodies. So, let's share my PPT first.
Yeah, you can share your PPT.
You can see my PPT?
Yeah, it is sharing. Yeah, it is visible now.
Yes, sir.
Yeah. The title of my talk is the aerodynamics of Bluff bodies. Here, this is itself a broad area. This aerodynamics means this word itself, it combines two words, air and dynamics. And the Bluff body in any obstacle, any body, where we can compare its streamwise length with its normal length. I mean the length in the normal direction. So we will discuss, I will give some brief overview, I mean, with the help of my current research area on the flow pass cylinders under uniform or non-uniform inlet velocity profile near a plane wall, plane boundary. And I work on simple, I mean, on the basic problem, because actually I'm not from the mechanical engineering background. I'm from mathematics. So I will try to explain some basic idea about this on simple two-dimensional lower Reynolds number laminar flow. I hope that basically it will be very helpful for those who are in the beginning, those who are interested to work in this area. And I will explain this thing here, basically this aerodynamics. Aerodynamics here you can understand like suppose an obstacle is there and if any object is there which is kept in the flow direction. So because of that flow, what is the effect on that obstacle? And suppose the vortex generation is there, what is the frequency and what are the forces acting on that obstacle? So I will discuss briefly with the help of basic examples, the flow pass cylinders. So as we know that, if you see here, there are some real life examples. For example, the offshore marine structures that we use for drilling in the deep water, and in the hazardous situations that it is very difficult to maintain their workability. So we design their structure like that. The effect of the hazardous situation is very less and we maintain our workability. And similarly, in the tall building, in the skyscrapers, if suppose there is only one building is there, what is the effect due to that incoming flow or the fluid present there? Or if there are more than one obstacle is there, I mean more than one buildings are there, what is the effect due to their position with respect to each other? And you can jumble this from this, for example, this compact heat exchangers. For example, in the computer, in your laptop, and nowadays everything is going to be very compact. There are very, very small chips are there which produce heat during their working. So suppose if you want to dissipate the excess heat from these small chips, what we do, we put some cooling, like suppose for example, we put some fan to dissipate that excess heat. So if we are interested to find what is the optimum position of that fan and that heated object, that we can dissipate that excess heat from that object. That this kind of study we can work on using this. We can study the aerodynamic characteristics here, and similarly the cooling of electronic components. Now, although all these real life examples, whatever I have shown here, these are characterized by highly turbulent, I mean high speed, three-dimensional flow. But as I said, because my working area, I'm working on the very small scale for laminar two-dimensional flow. If we do this kind of early initial studies, it gives some idea to predict or work on these real life problems. So all these examples, real examples, are characterized by highly turbulent three-dimensional flow, but still some basic information can still be gleaned from these basic problems. So as I said, suppose there is only one object is there in the flow. So because of the different, the type of incoming flow or that position of that single object, we can access the, basically this kind of studies are very helpful for the designers and engineers when they design these structures for longer sustainability of these structures. So for example, here, I will introduce the problem here. Suppose this one object is there. Suppose this is my Bluff body. Single object is there, which is kept at a fixed height from the wall. This is bounded by wall. And as I told you that the flow around this object or the forces acting on that object, in fact, they depend on the position of this object with respect to this boundary and the inlet velocity component. I mean, what kind of inlet flow profile is there? There may be different kind of flow, because always you will not get the uniform flow. I mean, whatever velocity at this location, that may not same at the upper or other locations. So this kind of, if at the inlet, non-linear velocity profile is there or parabolic velocity profile is there. So what is the effect on this obstacle we can study here, and what is the position of this obstacle with respect to this boundary region. So you can, and also if there are multiple structures, suppose this is my one object. If there are more than one objects, this is the example of two objects. So we can study what is the effect due to this presence of this upstream object, because flow is from this direction and this is my main object. So what is the effect due to its position? Position of this upstream object. Position means position with respect to this main object and with respect to this boundary and its shape. It may be a rectangle shape, square shape, or circular shape. It may have different shape. So what is the effect due to this upstream body in its position, and because of this inlet different velocity profile, what is the flow structure around this main object, and what is the effect on the forces acting on this main object? So here, I will show one simple example here. This is, suppose there are two cylinders. There are two long cylinders are kept in the flow, and physically there is only one boundary is there. It is bounded by one wall here. And at the inlet, this is an example of uniform shear flow. At the inlet, suppose uniform shear flow is applied. Then we are interested to see what is the effect due to the position of this upstream obstacle on this downstream square cylinder. Because this is the three-dimensional view. So, but I just told you I am working on the basic problem. So if you take the cross section of this cylinder, the picture will be like this. If you take the cross section of the cylinder, and suppose this is the example of a single square cylinder is there, and it is bounded by one wall is there, and at the inlet, non-uniform velocity profile is applied. So actually, physically, there is no boundary at the top and at the outlet, but it is bounded only from this bottom side. But as I said, because this is the example, because I have simulated these results using, if you remember, in the first day of this FDP, the presentation by Professor Anwar from EMU on the basics of computational fluid dynamics, simply giving an example, whatever he discussed about the method and CFD, this is the simple example of flow past cylinders. So here, you can compare with the real life problems. Here, it is bounded, suppose this is my computational domain, and it is bounded only from this bottom wall, but others are open. So I'm using the help of the CFD to find the solution in terms of what is the effect of this on this square cylinder due to its position with respect to this bottom wall, which is a stationary wall, and due to this inlet velocity profile. So if you are using the help of the computer, suppose you are a beginner and you want to work in this CFD area. If you have some basic knowledge about mathematics, and you are expert in some programming, if you know some programming language, and you know something about this problem of the physics of the problem, and then you can simulate these. Either you can write your own code, or nowadays many commercial packages are available like NCS Fluent. You can do this work there also. Whatever I'm presenting here, this for this single square cylinder, I have done this using my own in-house code. That we developed this code for this single cylinder here. So because first I will tell you this. They are the governing equations. I think you are already aware. They are based on the conservation principles. Basically, we are solving these equations in this whole domain. If this is my whole domain, we are solving these equations in this whole domain. So, but as I said, because we are taking the help of the computer don't understand these equations because these equations are highly non-linear partial differential equations. So first we need to convert these equations into simple algebraic equations so that the computer can understand these. So that process is called discretization. So what we do here,
Hello, sir.
What I'm going to present in this example. Here, this one single cylinder is there. Yes, sir. Can you hear me?
Yeah,
there is some audio. Yeah, now we can hear, sir.
Okay. So I was giving this one example of a flow past a square cylinder. You can imagine like this is a single Bluff body, which is placed at different gap height L from this stationary wall, and at the inlet, different inlet velocity profile is applied here. That is using this equation. This type of flow is called quasi-positive flow. Here, for different, if you see this in this equation, this is depending on this P. As we vary this P, the nonlinearity is increased at the inlet velocity profile. So we are interested to see what is the effect due to this inlet velocity profile and position of this obstacle of this single Bluff body with respect to this wall on its aerodynamic characteristics. Means on the forces acting on this obstacle, or if flow is unsteady, then what is the setting frequency for this around this square cylinder? So as I said, we are solving this we are finding the numerical solution for this physical problem. So we are taking the help of the computer, and we wrote the our own in-house code. There as I said, these are the governing equations which are highly non-linear partial differential equation. Computer don't understand these equations. So first we discretize these equations into, we convert this equation into simple linear algebraic equations, and we solve using some techniques. So, and we are solving these equations in this whole computational domain. So this is my domain. So we are solving these equations in whole computational domain. So in CFD, what is the first step? First we identify our problem, then we create the geometry. Okay. And the geometry, the question arises now, what should be the length of the obstacle from this inlet profile, and from what should be the outflow boundary condition, and how much distance should be the outlet boundary, and what should be the upper top boundary. As I said, because this obstacle is bounded only from this bottom wall, and so we are varying this height of the cylinder from this wall, but it is unbounded from this top and this outlet and here. So we choose this length, top length, and this downstream length, such that the effect of these boundary conditions on the velocity pressure gradient around this square cylinder is very less, so that we can better resolve, or we can say we can better assess the solution around this. What is the flow behavior or forces around this square cylinder? Because when you can understand the problem like that, because there is only one cylinder is there, and it is bounded by only from this bottom wall, but this is open. But we have to tell the computer somewhere to cut that boundary. Actually, in physics, in physical problem, there is no boundary from this top and this downstream side. But because we are taking the help of this computer and we are solving this numerically, so we have to put these boundary conditions and we have to tell the computer that cut to this boundary. So suppose this is my whole computational domain. So what we do, we solve these equations at this whole domain. So first step, we discretize this whole computational domain into small meshes. So this is the method. Here I have used these methods to solve these governing equations. I have used the finite volume method. And these discretized equations, we solve this using simple method that's proposed by Bhat. So first, in the first step, what we do, here, so this was my computational domain. So first, what we do, we discretize this computational domain into small meshes. The small nodes you can see here. And if you see carefully this figure, in this figure A, near this render surfaces, very fine, very dense meshes there. And as we move far from this body, increase the mesh size, coarse grids are taken. And in this figure B, this is the zoom view. Near the surface is very fine grid. And if you move to the far region, some coarse grids are there to capture the actual physics. Because my aim is to capture this area around the cylinder. So I have taken the very fine mesh near this object. So now how to solve this mathematically, I will not go in detail here. I will give them overview that I told you I use here finite volume method for this spatial discretization. And once we discretize, we generate the mass, then we have to store. Now how will you store there? If you see those equations carefully, there we have to calculate the velocity and pressure component. Here velocity is the vector quantity. That this is the example of U control volume that we have created this mass. In this mass, how to store this vector quantity, the velocity quantity that we stored at the cell surfaces, the middle of the cell surfaces here, and the pressure or the scalar quantity at the cell center. And these were the equation. We can write this equation in this form, these governing equations, the numeristic equation, and we are converting this equation into simple algebraic equation. So for that, we use different finite volume method, and for discretizing different terms, we use different tools. And we discretize this for, first we integrate this at the next time level. So I think you will confuse you, I will not go into detail here. And if you discretize these equations, which are based on the conservation principles, then this is the example of, and for this, we have used here third order upwind scheme for discretizing the converting terms. Once we discretize these, you will have this kind of simple algebraic equations that you can store in form of matrix. And from there, you will find the solution in terms of velocity and pressure at a particular time. So once you discretize this, either you write your own code, or you can take the help of these commercial packages like ANSYS Fluent and Star CCM. There are many commercial packages that are available in the market. So once you store these values and they appear in this simple algebraic form and solve this in matrix, and you get the solution in terms of velocity and pressure. Once you get that, then after that, with that help, you can, whatever post-processing you want to do, whatever physics you want to capture, you can do that and make some conclusion based on that. So here, this finally it came in this matrix form, tidal form, and by the back substitution, you can find the solution. Now, because in the first step, what we did, we first create the geometry, and we do the spatial discretization. We discretize this whole domain into small nodes, or you can say meshes. Now the question is, in general, you can say, commonly it is said that if your mesh size or the grid size is very small and time step size is very small, then your solution will tend to the exact solution. Because so far, these equations, exact solution is not known to us. This is the open problem. So that's why we go for the approximate solution, or you can say numerical solution. But we try to make that solution very near to the exact solution. So if your node size and the time step is very small, then we believe that our solution will tend towards the exact solution. Now the question arises, if I will make very large number of nodes and my time step is very less, in that case, need more computational power and it will take more time to compute the solution. So for that, first what we do the grid independent and time step study, because we cannot increase infinitely the number of nodes and time. Or take the less time. So because of the limitation of our computational resources. So what we do this grid independent and time step study, where we find the optimum number of node and optimum time step. If you see in this table, for this particular problem, what we did, we choose these 5 different combination of nodes. We discretize this whole domain in these 5 different combination of nodes, and see what is the effect due to change in these nodes and time step on the flow characteristics. Here now in this column, this ST is the setting frequency. And if there is a vertex generation in the flow, then what is the frequency of the vertex setting, ST? And CL prime, this is the RMS of lift coefficient. Now, what is lift coefficient? First of all, what is lift force? Lift force, that is the force which is acting on the body in the normal direction. And so from there, we can calculate the fluctuating lift coefficient, that is CL prime. And in the last column, this fourth one, that's CD bar, that is the average drag force. This is the average drag force coefficient. What is drag force? Drag force is the force acting in the flow direction. Suppose there is one body, so if the flow is from this one direction, then the CD bar or the time average drag coefficient, this is the coefficient which is acting on the flow direction. And CL lift is the force acting on the normal direction of the flow. So here, what we did for different combinations and for different time step, we did this time independent and mesh independent study. So, and for different combination, what we observe here, for the lowest number of nodes, that this stall number is 0.1154, as we double the number of nodes, there is a change of 0.65% in this stall number. Further, if we increase the number of nodes, the change is 1.27%. And further, if we slowly, if we keep on increasing the number of nodes, now the change is decreased here. And similarly, if we change the time step here, that I mean from this overall, from these different combinations, what we optimize our nodes, and we get some basic idea that okay, this much of nodes or this time step is sufficient to get the right solution. So from this I have highlighted this combination of nodes and the time step for this number of nodes for this particular problem. What I found that this combination is optimum one. For that, there is no after a further change in the node, there is not much change in the results. Results here, this aerodynamic characteristics, forces and frequency. So once you found this optimum number of nodes, now with that you can go for your further solid simulations. Now, once you model your problem, you have done this discretization and meshing and grid independent study. Now to get confident that my results are right or not. So for that, what we do, we compare these results with some earlier published work or some experimental work. Because now, what is the beauty of this CFD nowadays? Because it is not possible every time to perform experiments for all the prototypes to be in the experimental laboratory. So for that, if we have the computational resources, then we go for this CFD here. So here, once you identify your optimum number of nodes, then we can compare these results with the earlier published results or with the experimental results. So it will give the confidence about your generated results. So once you've done that, then whatever study you want to do, whatever parameters you have in your study, that you can do. For example, here, for the single cylinder case, there, as I said, I have varied this L. L is the height of this cylinder from the wall. Because in physical problem, there is only one obstacle is there, and which is bounded only from the bottom wall. Only one wall is there, which is kept near this cylinder. And from the other side, it is open and flows from this direction. So we are interested to see what is the effect due to here this P for different P. P is the, as I have shown you that in the flow configuration, when we increase this P, we are increasing the nonlinearity at the inlet. So what is the effect due to this nonlinearity at the inlet and due to this different position of this single cylinder with respect to this wall on the flow and flow characteristics? Here you can see when the cylinder is very near to this wall, the flow remains steady. There is no fluctuation in this wake region. It remains for this L.5, and the cylinder is at 0.5 height from this wall. I mean, there is no fluctuation in this in the flow, and the flow remains steady. And it is up to this L.5 for P equals to 1. But for P equals to 1, when we increase this gap height at 0.5, as you can see clearly what settings there from the wake. And further, if we keep on increasing the gap height and this this nonlinearity at the inlet, you can see the unsteadiness can be generated at the lower when the cylinder is very near to this bottom wall. Some fluctuations can be seen in the far back region, but near the cylinder, still flow is steady. But as we increase this gap height, the flow is now fully developed. And further, if we increase this height of the cylinder from the wall, you can now see regular vertices are observed, and the vertices from the lower side of the cylinder, they are stretched. So if we further increase this L star, I mean the gap of the cylinder from the wall, and nonlinearity at the inlet, flow is become more complex, and regular and stretched vertices can be seen. So overall, if we classify all these vertices in this L star and P plane, because we are doing in here for different gap height and for different inlet velocity profiles, we have identified 4 different patterns here. When the cylinder is very near to the wall, for lower gap height, here the flow remains steady. It can be seen identified from this lift and drag signals. And if you increase this gap height, here unsteadiness can be seen, regular vertices from this upper side of the cylinder, but from the bottom side there is no vertices. That's why I used here the notation W UR plus L0. Which means from upper side regular vertices, from lower side no vertex. And further increment in this L star and this P, here the regular vertices are seen from this upper side, but the stretched vertices, this red color from the bottom side of the cylinder, they are stretched. So this kind of pattern we have given this name WUR. UR means upper side regular plus lower side stretched. And for the higher gap height and higher value for higher nonlinearity, you can see this flow. The signals of lift and signal, they are very irregular, and the flow is, I mean, from the upper side it is regular, and from bottom also it is regular. I mean, the wall effect is reduced here. So you can see here from this study, so how the position of the cylinder and how the inlet velocity profile affect the flow around this single Bluff body. Now this can be explained from this help of this gap flow. This is the singles. This is cylinder cap at different gap height from from wall. So at this is the velocity profile drawn at this location, particularly this location. This figure A for P equals to 0. When it means when the inlet velocity profile is linear. So what is the gap flow here? You can see here when the flow is steady, that maximum velocity is near the middle of this region. When the flow becomes unsteady, that the maximum velocity, this point lies near to the bottom surface of the cylinder. It means for the larger gap height, this and larger, I mean this non-linearity, flow is accelerated near the bottom surface. So this figure B for larger, I mean P equals to 5 for higher non-linearity, you can see the magnitude of this velocity. This is around 3.5 here for P equals to 0, and here for P equals to 5 for higher non-linearity here. This is around 2 point something. I mean it is remarkably increased by increasing the non-linearity at the inlet. And these are the spectra of the lift coefficient. I mean, what is the intensity of the peak of the spectra in different 4 regimes we have classified earlier. So for different, you can see here for when the upstream side, for upper side, the regular vertices there, and from lower, no vertices there. There will be a small peak with a smaller stall, lower frequencies there. But as we increase the gap height, when the regular vertices is there from upper and stretch vertices from the lower side, then the prominent peak is there with largest frequency. Similarly, if we increase this nonlinearity, this for P equals to 1, 3, and 5 at the inlet, this peak becomes more prominent, and its subharmonics are also present here. Now, this is the effect on the aerodynamic characteristics. Here, this figure is for the Stall number, that is, you can correlate with the previous slide from the spectra of the lift coefficient. You can see in the first region, when the flow is steady, this is 0 here, and the maximum Stall number or the frequency is observed for this combination of this P and L star. Here the frequency is larger, and as you can see here from here, as we increase the nonlinearity, the frequency is increasing. And this figure B, this is the time average drag coefficient. What is the effect on the drag force acting on the cylinder? As you can see here, when the cylinder is near to the wall, this the drag force acting on the obstacle is very less. But as we move the cylinder in the far region and we increase the nonlinearity, the average drag is more in this area, in this region 4. And similarly, this is the fluctuating lift coefficient presented in C. These are the control plot for fluctuating lift coefficient. It follows the almost the same pattern of the average drag coefficient. So from this example, what we understood that this inlet velocity profile and the position of this obstacle, it matters a lot for the studying the aerodynamic characteristics. I mean, it has a remarkable effect on the forces, frequency, and the flow structure around this single obstacle. Now, I will tell you one more example. When this is suppose my main obstacle. If you keep another obstacle in front of this is the example you can send. A lot of studies are going on this. Suppose we have to control the flow around this flow and forces around this downstream main cylinder. Then if we put another cylinder, we can control over this passively. There are two ways to control the flow and forces around this main cylinder, by actively and passively. In active problem, we have to put some external energy source, and in the passively, whatever resources we have, by making the changes there, we can control the flow and forces on this main obstacle. So here, this like the earlier problem, this is the single cylinder is kept here. Now we have kept another obstacle in front of this main cylinder, and we are interested to see what is the effect due to presence of this on this downstream gas cylinder. And these are the boundary conditions are same like that, but here at the inlet we have applied the uniform shear flow, and here the wall is there. And I would like to first mention this S here. This S is the distance between these two cylinders, this horizontal distance between these two cylinders, and this L is the height of the cylinder from this stationary wall, while this downstream cylinder, it is kept at a fixed gap height from the wall. So we are interested to see what is the effect of the position of this upstream cylinder on this main object. I mean, effect on this flow and aerodynamic characteristic of this main downstream cylinder. So here, for this problem, these are our parameters. The Reynolds number is fixed, and the spacing between these two cylinders is varied from 0.5 to 7. And the position of this cylinder with respect to this ball, it is varied from 0.1 to 3. So, like the single cylinder example, we have done this for different combination. These dots shows these the position of this upstream cylinder for different combination of this S and L. We have done these simulations, and we have to see that what is the effect. You can see here, we have similarly we have classified different flow patterns here. For this, below this red line, this red dot dash line, the flow remains steady. I mean, the flow from this main downstream cylinder remains steady for this location, or for this red location of upstream cylinder. But as we move the cylinder away from the wall and from the cylinder, flow becomes unsteady. And if you see in the second pattern, for when cylinder is near to this downstream cylinder but slightly separated from this wall, this because of this lack of spacing between these two cylinders, the upstream cylinders shearless, they don't evolve, and they don't set the vertices in the gap region. They envelop with the shear layers of the downstream cylinder, and finally one single streak from the wake of the cylinder. And further, if we increase the spacing between two cylinders, you can see now the spacing between two cylinders is sufficiently large so that vertex shedding occurs between these two cylinders, and finally it merges with the downstream shear layers, and only one single row of vertices can be seen from the downstream side. And in this fourth region, here now this cylinder is now far from this wall. Now there is because of this first flow here, the lower shear layers from the upstream cylinder, they are stretched, and ultimately from the downstream region, again we got the single row vertices, and the downstream cylinders, this lower shear layers, they are stretched here. Now in this fifth region, when cylinder, this S star, means the horizontal length between two cylinders is still less, but this cylinder is kept far from this wall. There you can see here, this wake-to-wake interaction occurs here. The upstream set vertices, they interact with the downstream set vertices, and ultimately the complex flow is there from this downstream region. And in the sixth region, when the cylinder, upstream cylinder, is far from this downstream main cylinder and from the wall, that you can see the stress vertices from this upstream cylinder and multiple rows of the vertices are observed from the downstream area. Now see what is the effect of this upstream cylinder on the aerodynamic characteristic of this downstream sphere cylinder. Here this figure A, this is for the setting frequency. Here for this first area, first region where the flow was studied, here there is no settings, very small vertex, frequency is observed here, almost negligible. And as we move the cylinder from the wall and through this cylinder, maximum setting frequency observed in this region, in the sixth, when it is very far from the wall and the cylinder, downstream cylinder. So because of that location of this upstream cylinder, the larger frequency is observed from the downstream main cylinder. And now further, in this figure B, this is the RMS of lift coefficient. Here, this maximum this fluctuation is observed for this fifth region where the wake of two cylinders interacts. The upstream vertices, upstream cylinder generated vertices, they interact with the downstream wake vertices. So the maximum fluctuation is observed for this fifth region. And similarly, in this slide is figure A. This is for the time average drag coefficient. This is normalized by single cylinder's value. Here you can see when this upstream cylinder, this L star is the gap height, the spacing between upstream cylinder and the wall. When the cylinder is near to the wall, this you can say this is when L is to 0, when this is attached to the wall. In this blue area, in the first region, when this upstream cylinder is near to this wall, then the drag experience on this downstream cylinder is very less. It is due to the sheltering effect. The position of this upstream cylinder, it shelters the incoming force on the downstream cylinder. Because of that, the drag on the main cylinder is reduced here. But as we move this cylinder far from the wall, then the maximum drag is observed for this fifth region from the downstream cylinder. It is because now in this fifth region here, the downstream cylinder is now directly exposed to the incoming flow. Because of that, the drag is increased on the downstream cylinder. And similarly in this P, this is the normalized lift coefficient. Here again, for this larger gap height and the fifth region, larger lift coefficient is observed for this downstream cylinder. And for inline, in that case, net lift is observed. It is because the viscous force is prominent in the near wall region. Because of that, so for some cases, we observe the negative lift force also. Now, this whatever I explained, I gave you two examples for single and two cylinders. What we observed that the flow and the aerodynamic characteristics of this main cylinder can be controlled due to position of its neighboring structure. That neighboring structure is position and the inlet cluster profile. And you can, as you have seen there, when the cylinders and when the objects are in tandem position, that the forces are remarkably reduced from the main cylinder. And when it is kept far, and basically what's the idea that at this low Reynolds number flow, from the previous study, what we observed that when a single cylinder is kept near a wall at gap height of 0.5, the unsteadiness generated beyond Reynolds number 125. But here, what we observed, by the presence of this upstream obstacle, we got the unsteady flow at this lower Reynolds number, which is lower than the critical Reynolds number. As I said, the critical Reynolds number was 125. But here, due to presence of this upstream cylinder, we got the unsteady flow from this main cylinder at Reynolds number 100 also. So we can conclude from this that this upstream cylinder can work as the controlling cylinder. You can say it can control the flow and forces on the main obstacle. So you can correlate this problem with the 3D, or I just shown you at the first slide that the example of the real life problems when multiple structures are there. So there we can get some basic information from this study here. Now I will tell you one last example here. When suppose there are two cylinders are there, this downstream cylinder is allowed to vibrate only in the one direction, but this upstream cylinder is fixed. So now, what we are interested to see what is the effect due to this cylinder on the vibration of this. Now, why I'm talking about this vibration of this cylinder, because earlier problems was for a stationary one, but here for this vibrate, recently this vibration of cylinders, this kind of structures has paid more attention, because nowadays this vibration, these problems are used for harvesting energy naturally. Whatever energy we are generating from due to this vibration of this cylinder, that can be converted as and harvest the energy. So this is the one basic example. So here in this example, suppose this downstream cylinder is vibrating in this y direction, and this upstream cylinder is fixed. And these are the parameters here, Reynolds number 100 and 200. And here, because it's a vibration problem, so we introduce new parameter here, mass ratio. This is for fixed mass ratio 3. UR, this is the reduced velocity. This non-dimensional velocity UR that we have varied from 1 to 30. And the spacing, two values between the two cylinders, 1 and 5. When cylinders are very near to each other, I mean for S star equals to 1, S star is the non-dimensional distance between two cylinders. And 5 when they are in the significantly far from each other. When they are very close, that it falls in the classical way defined, we classify this as the reattachment region. It means what the shear layers from the upstream cylinder, they reattach on the downstream cylinder without setting vertices in the gap, if the gap space is very small. If the gap space is larger, then before attaching to this downstream cylinder, it will set vertices in this gap region. So corresponding these two regions, we have considered here two spacings, 1 and 5. Now here, this model mathematical equations are similar to the previous one, but only we have added one more equation here for to capture the vibration of the cylinder. This y double dot, this is the acceleration. I mean, this y is the displacement of a cylinder from its mean position. When you can imagine, like when the cylinder is fixed, how much vibration is there from that cylinder, and this y dot is the velocity, y double dot is the acceleration, and the CL is here the lift coefficient, and Mr. is the mass ratio. So I'm not going to detail in here. Simply I'll come to the results here. And here similarly, the way we discretize the previous problem, here also we discretize, but here, because this is the vibration problem, so we create this one moving zone that actually for this third example, we have simulated that using ANSYS frame there. We generate this which special care has been taken for this moving zone to capture the physics here. And now here, these are the results when only one single cylinder is there in the domain, which is vibrating, and this result for at close number 100. Now in this figure, this is for corresponding different reduced velocity, and this is the A star is the amplitude of this vibration. The cylinder is vibrating at what is the the amplitude there. So you can see here, if you know something about this in this area, that this is a classical way to identify these branches. I mean, based on this this vibration of the cylinder, we classify in different branches. This first one is the initial branch when the vibration is initiated, and this is the lower branch, decline, and then desynchronization. And this area, this portion is called, you can say, synchronization region, and this is desynchronization region. And you can understand like that. Suppose you're working on a cylinder. If you give some initial displacement there, if you change in the frequency, it's also making change in that string mass system, then it means that is synchronized with your initial input, so that it falls in this synchronization region. But if there is no change, that is in the desynchronization region. So based on this amplitude, we have classified in 3 different categories here. So you can see here corresponding the flow structure. As the initial branches is initiated, what is the flow structure here for this corresponding reduced velocity 4? And in this synchronization region, when this amplitude is larger for this particular problem, what is the flow structure here? Just 2 pair of vertices setting in each cycle. And similarly, in this lower branch, when this amplitude decreases, how the flow structure changes from this peak. And in this desynchronization range, now you can see here how this is different from this lower branch here. This spacing between these consecutive vertices, this spacing is decreased here. So you can correlate this thing. This is the previous figure for the amplitude here. You can correlate with this Stahel number setting frequency here. I just told you this initial and lower branch, this is in the synchronization area. synchronization range. Here in the synchronization region, because by making this, and here this black color, this dot dashed line, this is for the stationary cylinder. When cylinder is fixed, in that case, this is denoted by ST naught. This is the setting frequency for the fixed cylinder. Now, when the cylinder is there, you're working on this vibration cylinder. So here in this synchronization branch, in this initial and lower branch, here with the change in frequency, here the frequency, it changes from the stationary value in both branch, initial and lower branch. But in the desynchronization region, there is no change in the frequency. It is same as of this stationary cylinder. Now further, if you increase the Reynolds number for the same problem when single cylinder is there, you can see for this initial and lower branch, the flow is same. I mean, the amplitude behavior is similar to the previous Reynolds number. But for the larger reduced velocity, you are greater than 12. Here the amplitude again, it is increasing. This we call as the galloping branch. In the galloping branch, the amplitude will be very high, and the setting frequency will be very less. So you can say this is the instability condition. Here, if you're working on real life problem, if you're getting this kind of pattern there, it means your system is unstable. So because here the amplitude is increasing. So I mean, what is novelty in this work? First time what we classify here, this we divide this galloping branch in. We have shown here, this is the combination of initial, lower, and initial branch and distribution branch. And there you can see the corresponding this velocity profiles and the flow characteristic flow pattern here. For this reduced velocity 12 to 24, here basically if you see, I have not shown here their corresponding amplitude and signals. They are basically a combination of small and large frequency curves. So if you filter those, and we got the combination of these two, initial and lower branch. That's why we have classified this galloping branch as the combination of initial and lower, and initial and distribution in these two different regions. Similarly, the way we classify for Reynolds number 100, we can classify this branching based on this Stahel number for this synchronization branch, initial and lower. There, this the frequency either less than or greater than that stationary single cylinder value. But in this galloping branch, for this 12 to around 24, that is combination of initial and lower, and for above 24, this is combination of initial and synchronization branch. This is one example of, I mean, so the first structure, then how the flow is evolving by changing this reduced velocity at this Reynolds number 200. You can see here this lift and amplitude signals. When the reduced velocity is 3, when the initial branch just started, both the signals are in phase. But as we increase the reduced velocity, sometimes this lift is lagging, or sometimes this amplitude, this Y is lagging. So because of that, you can see there is the amplitude is not fixed in these signals. And further, if you increase this reduced velocity at UR equals to 5, we've got two different kind of patterns. You can see you can classify in two different branches. One this where the amplitude is larger, and this one where it is lower. So corresponding, we have two different flow patterns. And further, if you increase this reduced velocity, they are in antiphase. The phase between they are in antiphase. The CL and the Y signal, the displacement signal, they are in antiphase. This is the example of this in the discrimination in the galloping branch, initial and lower branch. As I told you, you can see here these signals, this the CL and the displacement signal. They are a combination of lower and high frequency curves. So by using this filtering technique, we filter these signals in lower and high frequency curves. Here you can see in the low pass filter, these signals are in phase. So that's why we call this combination as, I mean, some initial branch property is inherent here. And for this high pass filter signals, they are antiphase. So that's why we call this as some lower branch property are inherent there. So that's why for this particular region, we classify this for combination of initial and lower branch. This is the flow structure during half cycle. In this, for UR equals to 30, in the maximum value considered in our case here, what is the effect due to this, I mean, flow structure in this one half cycle that is explained here. Now, if you put this upstream stationary cylinder in front of this vibrating cylinder, what is the effect on this vibration of this downstream cylinder? This is a single cylinder. First, I told you that basically based on this amplitude and the phase lag between the amplitude and the lift signal, we classify these different branches here. Let's keep here. This is the average drag force acting on that. I would directly come to this point. When we put this stationary cylinder in front of this vibrating cylinder, you can see here for this Reynolds number 100, this first figure for Reynolds number 100, there is not much change. Only the initial, this branch is delayed because of the presence of this upstream cylinder. Because this black color is for single cylinder and this red for the downstream cylinder in presence of this upstream stationary cylinder. So this branch is delayed here. But if you see here for this 200 case, when there is only one single cylinder, we observe the galloping branch. For this area, that amplitude was very high, but due to presence of this upstream cylinder, we didn't get this galloping branch for this big cylinder here. But the amplitude is increased here. And this now these were the results when the cylinders are placed very near, when the spacing between these two cylinders is 1. Now further, if we increase the spacing between two cylinders, that as I discussed that this fall in the coinciding region, where the distance between two cylinders is enough now that this upstream cylinder set the vortices before attaching to the downstream cylinder. So because of this stationary cylinder, you can see here the amplitude on the wake cylinder is increased remarkably compared to the single cylinder. I mean, when there's only one single cylinder is there at Reynolds number 100, now if you put this another upstream cylinder, because of that, the amplitude is increased remarkably for this downstream cylinder. And corresponding, you can identify the phase between the lift and the displacement signal here. In different branches, they are either in the phase or in anti-phase. Now, similarly, if you increase the Reynolds number to 100 to 200, now further you can see, compare the amplitude curve. It is increased more compared to the Reynolds number 100. Now it is increased from, if you see the previous slide, there it is a maximum peak around 0.7, amplitude is around 0.7. Here it is around 1.3 something. So it means, as we have seen here, as I told you, in this synchronization branch, whatever, I mean, because at this low Reynolds number study, we observed the larger amplitude fluctuation in this big vibrating cylinder, which is a remarkable, you can say, in terms of harvesting the energy from this sources. Because in this synchronization region, if you're getting this larger amplitude, that which can be converted for the harvesting the energy in this low Reynolds number flow. Because although I told you that in the real life problems, these are for larger Reynolds number, high speed flow. But we are getting these things for this lower loss laminar flow also. So we can conclude from this example that if we put this upstream cylinder in front of this downstream vibrating cylinder, we can generate the larger, we can harvest more energy, especially in this co-setting region. It means when this distance between two cylinders is sufficient that the vertex generated from the upstream cylinder, they affect the vibration of this cylinder. Because of that, the larger amplitude can be observed from the cylinder, which can be used to so this all about dynamics. Yes, sir. Thank you, sir. That's all from my side.
Yeah, thank you, sir. Is there any questions from the participant side? You can write it here in the chat box, or you can raise your hand. I can unmute you.
Thank you, Dr. Rajesh Bhat. A wonderful lecture.
Thank you, sir.
Just my one question. This, whatever you have done, this Reynolds number 100, 200, this is for especially for laminar flow, right?
Yes, sir. This is only for laminar flow.
Okay. So this bluff bodies is applicable for turbulent flow also?
Yeah, for turbulent flow, that model will be changed because these mathematical model, whatever I have considered here, that will not applicable for that case. And the solution strategy also will change.
Okay, okay, okay. So wonderful presentation. I think a lot of mathematics are there. I've seen that a lot of mathematics will be reduced also. Thank you very much for your wonderful presentation. So I will ask participants if they have any question, please let's post it here. And I think maybe there is some network issues was there. So sometime in between, but overall it is went well only. Maybe small disturbances came in that in between.
Yeah, that is net issue from my side here.
Yeah.
I'm using my mobile network.
I think nobody having any questions. Maybe because mostly it is simulations and most mathematics are there. Most of the participants here are mechanical engineers. But I request Dr. Rajesh to just, if possible, you can share your email address so that if anybody future having anything in simulations, maybe they can contact.
Sure.
And I think I need to highlight here one more thing. Yeah, he's typing in the slides. Please note down rajesh.bhat@vit.ac.in. So because Dr. Rajesh is very good in simulations. So here today's two speakers. So first speaker, Dr. Arun Kumar, he is good in experimentation. And second speaker, Dr. Rajesh, is very good in simulations. So I think actually we plan in such a way that it can be go well to the audience so that they can understand experimental first and then simulations. And thank you very much, Dr. Rajesh, for your valuable time and your efforts to deliver this wonderful session in today in our FDP program.
Thank you, sir, for inviting me for this valuable FDP. I hope that at least for beginners, those who are interested to work in this area, CFD, I discussed the very basic problem. If you have any query regarding the simulation mathematics behind that, you can write me mail also. No problem.
Yeah, here I've seen the feedback. A lot of participants has given wonderful feedback because you maybe you are good in mathematics, but you are focusing on basically basic fundamentals of the simulations. I think audience are very much appreciating. Thank you very much. And I request Umair Ansari just take this stage and if possible conclude.
Yeah, sir, yes. Sir, there is one question.
Yes, sir.
Any possible positive application of wake behind bluff bodies?
Yeah, that as I told you that because our interest was to observe the wake flow around this main cylinder. As we have seen that because of this upstream cylinder, the flow structure is disturbed around this downstream cylinder. Because of that wake flow only, there is a change in the aerodynamic forces or frequency of this vertex setting of the main downstream cylinder.
Yeah.
So as I told you, at the beginning, I told you that suppose if you want to dissipate the excess heat from the main, suppose that my main cylinder is suppose heated one, and if I want to dissipate the excess heat, so because of this unsteady or the wake region created, we can access that whether for what condition that there will be more or maximum heat transfer. We can correlate with that. This is one small example I give.
Yes. Yeah, sir. Thank you, participants, for your comments and your questions. And last, I will give a vote of thanks. Thank you, sir, for your valuable lecture and session regarding bluff bodies and vibration of cylinders and about the unsteady and steady flow patterns. In spite of your health is not feeling well, you given us time for your session. Thanks from the department and personally, thanks, sir. Thank you, sir.